Section 12.1, extra example number 2, tipping at a buffet. So we are going to do with this problem a significance test with the slope of the regression line. So the data here is about tipping at a buffet, and the question we're asking is, do these data provide convincing evidence the customers who stay longer give larger tips? Looking at this data. So here's a scatter plot of the data with the least squared regression line added. Describe what the graph tells you between the two variables. So this is, we could have done this back in chapter 3 in looking at this data here. So we would say for part A that there is a weak positive linear association. Looking at the least squared regression line, there is a, it's weak because the data points are not that close to the line, but it still looks linear, and it's a positive association. The slope is positive. There is a weak positive linear association between the explanatory variable, which is length of stay, and the response variable, which is the tip amount, So the people that stay longer tend to give larger tips, but that's all we can say there. Okay, so then moving on, we're looking at some output here from doing a regression analysis, and we have the coefficient, the constant coefficient. This is your y-intercept here, this is your slope, here's the standard error of the slope, here's r squared, and here's the standard deviation s of the residuals down here. Here's the residual plot. This is if you take the residuals, if you plot the z-scores. So we're asking for part B, what is the equation of the least squared regression line, and define any variables. So that would be, for part B, is the equation. We just used the data, so it would be y hat, because that's what we use for the predicted response, is 4.535, the y-intercept, plus the slope 0.030x, where y hat is the predicted tip amount in dollars, and x is the length of stay in minutes, and length of stay in minutes. So then for part C, we're asked to interpret the slope and y-intercept. What meaning does that have? So for the slope, it means for each additional minute, remember the change in x is always by 1 for slope. Slope is change in y over change in x. So for each, the slope means for each additional minute, that a party stays at the buffet, you can use this abbreviation. The least squared regression line predicts an increase, and that's, the slope tells us, of 3 cents. So for every minute longer they stay, they're going to tip 3 cents more, 3 cents. And the y-intercept means that's a party that doesn't stay at all. And so does that make sense that the amount of $4.53, would that be a reasonable value there? And if you go back and look at the data, does anyone stay, are there any data points for time 0 minutes? Does anyone stay? Okay, yeah. So we're shaking our head no. So a party who does not stay, a party who stays for 0 minutes, we'll leave a tip of $4.53 roughly. And that's called extrapolation when you use data values that are outside of a reasonable range. So you would say this extrapolation is unreasonable. Because if someone left right away, they're probably not going to leave any tip at all. Unreasonable. So we wouldn't use that. And now finally we want to answer the question that we started out asking, which is is the length of stay, does the amount of tip increase the longer you stay? So we're going to carry out a test for that. We're going to do a state plan do conclude. So for part B, so you would state, and this is like you'll be doing in your homework, let beta, that's the symbol we use for the population, the slope of the population, least squared regression line. Let beta be the slope of the population least squared regression line that relates length of stay to tip amount. Relating length of stay to tip amount. And so our hypothesis is that for H0, we would say that the slope is 0. So basically the least squared regression line doesn't help us at all. And if we can reject H0, then we can say that the slope is positive, and that would show that the longer you stay, the more you tip. So that's our state. In the plan, we're going to go through all the 5 conditions together. So for the plan is to do perform a t-test for the slope. Perform a t-test for the slope. Beta at a significance level of 0.05, since we weren't given one, if the 5 conditions are met. Number 1, data is linear, and so the scatter plot did show a weak linear relationship. So we are okay for that. So the scatter plot shows weak linear relationship. Next condition, independent. So knowing one tip amount shouldn't provide information about the other tip amounts. They're all independent results. One party that was there isn't talking to the other. And we can assume there are at least 120 receipts. So even though we're selecting without replacing, it's okay. So there's 2 parts to this. Knowing one tip amount doesn't affect the other. Knowing one tip amount shouldn't provide information about the other tip amounts. Shouldn't provide info about other tip amounts. And also, since we're selecting the receipts without replacement, we need to assume there are at least 120 receipts, because we're selecting 12. Assume there are at least 10 times 12, or 120 receipts total. Okay, so that's, and then normal. We looked at earlier, there's a normal probability plot, looks roughly linear. That's the plot of the z-scores. So that's your normal probability plot. on your calculator, that's in the same place to do a scatter plot. Normal probability plot looks roughly linear. Equal variance, that's the standard deviation of the y values. So the residual plot shows a fairly equal amount of scatter around the residual line. So roughly that variation in y is about the same for any x value. So the residual plot shows a fairly equal amount of scatter around the residual line. That's that horizontal line. And finally, random, the receipts were selected at random. Random receipts were selected at random. Receipts selected at random. Okay, we're ready for our do section. So do is, we look at the computer output, which is what you'll be doing in everything today. From computer output, if you go back, the test statistic is given. It's the t. So test statistic t for the slope equals 1.23. Let's go back and look and make sure we know where that is. Right here, the test statistic under t for slope is 1.23. The p-value is also given. However, here's where you have to be careful. The p-value given here, the 0.247 given, is for a two-sided test. So that would be if our alternative hypothesis was that the slope is not 0, then we would use this. But since it's a one-sided test, it's just greater than 0, we have to cut this in half, because the computer output is giving it for a two-sided test. So take 0.247, so you go 0.247, cut it in half, and I'll make a note here. Since it's only a one-sided test, so that's equal to 0.1235, and that's our p-value. And so our p-value is greater than 0.05, so we fail to reject H0. And when you fail to reject H0, it doesn't mean you can conclude really anything. Since the p-value is greater than 0.05, we fail to reject H0. So we do not have convincing evidence. We do not have convincing evidence. Parties who stay longer give bigger tips. It's just in the sample that we took, it appeared it could have been that way, but statistically speaking, we cannot conclude that. So we do not have convincing evidence. Parties who stay longer leave bigger tips.